Dr. G.K. there to speak on thermophysical properties and phase transformation behavior of thorium-based alloys and oxides. Dr. G.K. Dey is the Associate Director, Materials Group, Bhabha Atomic Research Center. He is an expert in the field of phase transformation, solidification, complete microstructural characterization, structure property correlation. With his vast experience in this field, may I request now Dr. G.K. Dey for presenting his talk.
Thank you, Chair, for your kind introduction, and good afternoon, ladies and gentlemen. The title of my today's talk is Thermophysical Properties and Phase Transformation Behavior of Thorium-based Alloys and Oxides. Before starting my talk, I would like to thank Dr. Vijayan and Dr. Nayak for giving me this opportunity to share some of the results that me and my colleagues have done with the audience, with the august audience here. The names of my co-workers are written here. Because it's a multidisciplinary nature, we have many co-workers to assist us in this work. This is the outline of my talk. The first section is introductory, where we, besides other things, talk about the necessity for evaluating thermophysical properties of this type of new fuel. Because one has to design the fuel, and for this purpose, you need the thermophysical properties. Then in the second section, I would also talk about producing the material on which we have worked, that is some aspects of synthesis. Then in the third section, I talk about the experimental methods that we have used for evaluating the thermophysical properties, which have been compared with the properties determined by theoretical approaches in the fourth section, and then the comparison results have been highlighted in the fifth section. And finally, we conclude. Now, we are on the fourth day of the conference, and this slide will probably be redundant on the fourth day, but all the same, for sake of completion, I'll just run through this. Advantages of thorium as a fuel: abundant, high thermal conductivity, reduced actinide production, greater chemical stability, and greater proliferation resistance. And these can be, these will heavily outweigh the few disadvantages, namely significantly less is known about the fundamental properties of thorium oxide. That is definitely a drawback, and I hope this contribution goes a little distance in solving that problem. And finally, there is still a little bit of proliferation issue with thorium. Now, why MOX or mixed oxide fuels? As many of the speakers during the course of this conference have said, MOX can be used in the existing reactors with very high burn-ups. And we have thorium oxide as one of the components. Then because of the thermal conductivity during normal operation, thorium-based fuels will operate with somewhat lower fuel temperatures and release less fission gas than CO2-based fuels. So this is a big advantage. And of course, the biggest reason for us Indians to use thorium is because we have one of the world's largest thorium reserves, and we have very little uranium. And thorium-based fuels are better for plutonium incineration as compared to uranium-based fuels. Now, why thermal property evaluation is important? Though it is obvious, but still I will highlight these points. The behavior of thorium-based fuel during irradiation is largely dependent on its thermophysical properties and their variation with temperature and burn-up. Experimental data on out-of-pile properties such as melting point, density, thermal expansion, and thermal conductivity are required for fuel design, performance modeling, and safety analysis. Because the thorium-based fuels have hardly been used. Uranium-based fuels have been in use for such a long time. This kind of data has been generated long back in case of uranium-based fuels. But for thorium-based, especially the mixed oxide fuels, this kind of data is still missing in many of the combinations. So thermal expansion coefficients, for example, is required. It's an important data for fuel designers for finding the extent of thermal stresses. Similarly, thermal conductivity data is essential to understand heat transport in these materials as well as to predict critical temperature conditions for reactor operations. So with that introduction, I move on to the second section, which talks about thorium extraction, because all the thorium that we have used is obviously made by us. And I'll just delve upon few slides, though there is a detailed presentation after lunch on this aspect. So my number of slides on this are very few. Now, thorium from oxide has been proposed for breeding to begin with, and this thorium oxide is made by decomposition of thorium oxalate, which can be obtained from monazite processing. Dr. Patra gave a detailed presentation on our monazite resources, and we are very rich in this area. However, is the thorium metal which is better for ensuring a better breeding, that is fast doubling time can be used by using thorium metal itself. The problem with thorium metal is highly reactive. As you can see in the elegum diagram, thorium comes way below here, and only calcium is actually more reactive than this thorium in this case. So it easily converts to oxide and refuses to go back to the metal. And the melting point of thorium metal is 1755, which is another problem from processing viewpoint. So that gives us three avenues for making the metal. One is the oxide as a starting material, the other is the chloride, and the third is the fluoride. And in BARC, we have developed processes based on all these three starting materials, and we have done some work in all these three. The first is oxide as a starting material. This work was done a few decades back. So oxide was reduced using calcium as the reductant, and what we could get is a product which is having 1% oxygen. So the oxygen level was slightly on the higher side, and this could be made into different shapes, for instance, a sheet by powder metallurgy. So the powder metallurgy route is better suited, because otherwise melting and casting this would require, for instance, if you want to do it by consumable arc melting, this will require special type of facility and we don't have any such facility with us. We have some experience of non-consumable arc melting of thorium at the moment on smaller sizes. If you want to alloy this thorium, you don't want this 1% oxygen. Okay, so we have to have much purer metal for making alloys with moly or zirconium. And the problem is of reducing this oxygen. One way is to have electron beam melting, so to remove this oxygen, but then along with this oxygen, thorium will also go away, and you'll start losing about 15% of thorium. So this is not a very attractive method for having an oxygen-free product. The second route is the chloride route, where we use the same process as is done in case of zirconium or titanium, which is the Kroll process. Take the thorium chloride and reduce it with magnesium or calcium, and this process has also been tried quite some time back, and some amount of thorium has been made. However, thorium chloride is highly hygroscopic, and you again end up with the same problem, that is having oxygen in the intermediate stage, and this oxygen will go to the product, and that's not the thing that we want. The other thing is the thorium produced by this method is thorium sponge, which is again very prone to oxidation. The international route is through the fluoride route, where you reduce thorium fluoride with calcium in the presence of zinc. The presence of zinc would mean that you get the product in form of a eutectic of thorium and zinc, which is a much lower temperature, and if you heat that, you can remove zinc and get a good quality thorium. We have not started on this. Instead, what we have done is we have used thorium fluoride and used calcium, and we have not used zinc. And here the temperatures will be higher, so that is the disadvantage. So there is a container problem, but we are about to overcome this, and this will be a good technique for making good quality thorium from the starting intermediates. Now, that was about extractive metallurgy of thorium. A few, one or two slides on the physical metallurgy of thorium, which again is very, very poorly explored. So most of the fuels of thorium will have other alloying additions, because thorium is having very poor mechanical properties. So you would end up adding one of these elements as an alloying additions from the neutronics point of view, and these alloys, we must know the physical metallurgy of them in the phase transformation that may take place in them. So this is the zirconium thorium system which we are studying here, and in this case, if you add zirconium, the beta phase field will be enlarged, and you may be able to retain the beta phase at room temperature in concentrations like 75 atom percent zirconium alloy. It may be possible to retain it at room temperature also. So this is the initial macro structure of the thorium zirconium alloy that has been produced in BARC. We are also studying ternary alloys, that is uranium thorium zirconium or uranium plutonium zirconium as fuel, as candidate materials. And the next slide shows a glimpse of the physical metallurgy or the transformation aspects in uranium 50 weight percent zirconium alloy, where you can retain the beta phase, and on aging it transforms to the omega phase. So this is one of the first few examples of omega phase seen in uranium-based alloys, and the high resolution image done in BARC showing the two different variants of the omega phase in this particular alloy. So we also have some experience of the interaction of thorium with the clad. For instance, this is thoria and zircaloy as clad here. This is the zircaloy microstructure, and this is the thoria microstructure. And we made a couple of these two to see how these two interact, and the results from that couple are shown here. So this is the zircaloy side, and this is the thoria side, and we could see that when the temperatures were raised in vacuum, thoria has diffused to the zircaloy grain boundaries. Thorium has diffused, and the thorium and oxygen contents could be seen in this viewgraph here. You can see that at the grain boundary, the amount of zirconium dips, the amount of oxygen and that of thorium increases. So this is one aspect which is of concern, because one may think of putting a sleeve to prevent the diffusion of thorium into the clad, which is not desirable. So why mixed oxide? Well, of course, the advantages have been discussed at the beginning, but there are problems. Thorium uranium is not so difficult, but thorium plutonium is not so easy to study, both theoretically as well as experimentally. The reason for difficulty in theoretical studies, for computational point of view, plutonium poses a challenge owing to the itinerant behavior of its 5f electrons, which requires treatment using advanced methodologies and computationally demanding resources. This is the problem to deal with plutonium theoretically. The experimental problem, of course, is plutonium handling is difficult. So one would like to substitute plutonium with a surrogate material like cerium. Cerium oxide has physical chemical properties which are very similar to those of plutonium oxide, and hence is used as a surrogate material for PuO2. So we have made the mixed oxide pellets by two routes, powder processing and pelletization, that is the POP technique, and the other technique which is developed indigenously, coated agglomerate pelletization technique. And I will not go into the details of this, because there is another talk to be given by Mr. Arun Kumar, in whose division this activity has been carried out. Just to give you a flavor of this activity, the sintering atmospheres have been changed, both for POP as well as CAP. We have used air as well as a mixture of argon and hydrogen, and you can see the O by M ratios are more or less the same by both the processes, but the density and the porosity contents differ, and this leads to change in thermophysical properties. When you measure them, you can see that there are minor differences which could be important. So now coming to the evaluation of thermal properties experimentally, the thermal properties like thermal expansion, for instance, has been estimated by dilatometry and X-ray diffraction. So this is a view of the dilatometry results. A vertical dilatometer has been used, and the heating rate from room temperature to this temperature in high purity argon atmosphere at this rate has been done. The accuracy of measurement is 0.1 micrometer. The coefficient of thermal expansion has been evaluated by this equation, where the L2 and L1 are lengths at two different temperatures, T1 and T2, and L0 is the initial starting length. So with this, the extension of thermal expansion has been evaluated both for thermal oxide, thorium oxide, as well as the mixed oxides which are developed here, and you can see that there is no big substantial difference in the values irrespective of the fact that it does contain the other element as well. And these values also agree very well with the earlier attempts of such a determination by this group of workers. We also have determined the thermal expansion by X-ray diffraction at room temperature and at high temperatures. This is a view of the X-ray diffractogram at room temperature of the different mixed oxides, and from the shift of the peak you can find out how much of the expansion has taken place, and then you can determine the thermal expansion coefficient from this kind of effort as well. So, that also has been done. Now, coming to thermal diffusivity or thermal conductivity, which has been evaluated by determining thermal diffusivity. So, for this a laser flash device has been used. A pulse of laser was projected onto the front of surface of the pellet, and the temperature on the other side of the pellet was measured as a function of time, and also the size of the pellet was considered, and this is a dimensionless parameter. So, using these three you can get the thermal diffusivity, which has been plotted here as a function of temperature for centered in air product as well as centered in argon and hydrogen. POP as well as CAP products have been done, and you can see slight differences, and that is because of the variation in porosity and density. So, this is all experimentally evaluated. The thermal conductivity is obtained from the thermal diffusivity, which was shown in the previous slide, and you need the specific heat data, which is evaluated from those of the pure components by the Newman-Copps rule, and this is the density. And if you put these two in place, you can get the thermal conductivity as a function of temperature. The thermal conductivity can also be expressed in this empirical form A plus BT, where A is scattering due to the presence of impurity and is independent of temperature, and B is scattering due to phonon and is a function of temperature. So, this is, you can express thermal conductivity in this form also with A and B parameters having different values. I will show that as well little later. That was about thorium CO2, but as I said, we have also studied thorium UO2, and here again thermal diffusivity of THO2 and THO2 UO2 MOX by determined by laser flash methods, and these are the salient aspects of the results. There was difference as compared to the POP and CAP process. It led to differences in thermal conductivity for obvious reasons, because there is variation in porosity as well as the density of these. The O/M ratio was not found to influence the thermal conductivity substantially. In fact, the O/M ratio itself was not very much different in all the samples that we have seen. Then I come to the thermal property evaluation by theoretical approach. Now, theoretical approach is very attractive. Without doing an experiment, you can find out what is the thermal expansion coefficient and also the thermal conductivity, and this allows us to probe regions where it is difficult to make the sample by experimental means. So, the approach here demands that you know the interatomic potential. So, this has to be evaluated, and this has its basis in the Newton's equation of motion, that is force is equal to mass into acceleration. And then for an ionic solid, we invoke the Bond model, which is ions within the system are considered to be a series of charged interacting particles with a partial ionic charge sitting at lattice sides. Fundamental interactions are Coulombic, and a very short distance electron cloud of neighboring ions repel each other. So, with these three assumptions, the parameters of interatomic potentials of thorium oxide, CO2 and mixed oxides have been optimized by matching calculated values of thermal expansion and bulk modulus with those obtained experimentally. I will just highlight these in the next few graphs. So, this is the expression for the interatomic potential. This is for long range interaction. These quantities are known for the different elements involved. However, for short range interaction, the expression takes this form. This is the Buckingham expression, and here we have three parameters A ij, B ij and C ij, and these are not known, and these need to be evaluated, and these evaluated values are shown here. I will just tell the methodology for evaluating these three. The methodology is the one which is discussed here, that is, the parameters of interatomic potential have been optimized by matching the calculated values of thermal expansion and bulk modulus with those obtained experimentally. So, we assume certain values for A, B and C and determine the thermal expansion and bulk modulus and compare them with the experimental values. If they agree, then the values of A, B, C taken are the values which should be in place. So, this is shown in the next view graph here. This is the lattice parameter as a function of temperature and this is determined both theoretically as well as experimentally, assuming certain values of A, B and C, and once the match occurs, those are the values of A and B and C which are taken. So, this is the lattice parameter as a function of temperature and this is the bulk modulus as a function of pressure. So, both these quantities are used for evaluating A, B and C and that is what is mentioned here. This is for thorium oxide and the same exercise has been done for the CO2 as well. The same exercise, the same set of parameters have been evaluated and have been compared with the experimental results. Now, the mixed oxide also we have determined the thermal, determine the lattice parameter and change of lattice parameter which reflects the thermal expansion as a function of temperature and these are the molecular dynamic simulation values for thorium oxide, the mixed oxide and these are the experimental values and you can see that the agreement is quite good. And these are the parameters used for the simulation calculation and these are self-explanatory. Then we come to thermal conductivity. After having discussed the thermal expansion in the previous slides, we now come to thermal conductivity of the individual oxides and the mixed oxide by MD simulation, because these in the earlier section were estimated experimentally. We are determining it by MD simulation, and for thermal conductivity one has to use the Green-Kubo formalism, which means an estimate of a transport coefficient relies on the integral of an accurate time correlation of the equilibrium fluctuations of the corresponding heat flux in the system. So, with that assumption the MD calculations have been done and this is the thermal conductivity as a function of temperature, and here also plotted are the values obtained by other researchers in this area and the agreement is reasonably good. This is for thoria and this set of values are for CO2 as done by molecular dynamics as well as by experiments done by others, and here again the agreement is shown to be quite good. So, in the final section I compare the results obtained by MD simulation and experimentation for these alloys, and that is shown both in tabular form and graphic form. So, here we have the thermal expansion as evaluated by dialectrometry and high temperature XRD and the MD simulation for these thermal expansion coefficient. The MD simulation results are for THO2 and also for all the other mixed oxides. They have been compared with the experimental results, and you can see that the variation between these, for instance, this is MD and this is dialectrometry, this is theory, this is experimentation. They are reasonably good agreement between these two. So, it says that theoretical calculations can be used for predicting the behavior of mixed oxide fuels as far as thermal conductivity and the thermal expansion results are concerned, and they can be used for modeling. This is for uranium oxide, this is the experimental and the theoretical values are plotted on the same plot here, and here again we can see that the agreements are very, very good. Here the instead of dialectrometry, high temperature XRD has been used. This comparison is for thorium uranium oxide determined by dialectrometry and high temperature XRD versus molecular dynamics. You can see the molecular dynamics results are listed here for pure thorium, thorium uranium oxide, and you can again see that the agreement between molecular dynamics and experimentation is very, very good. So, this would indicate that the approach used is correct. The observations have been summarized here, and I will just run through this. Calculated lattice parameters of thorium oxide and MOX are matching well with experimental measurements in the temperature range 300 to 1500 K. The calculated decrease in lattice parameter as a function of the ionic contents of these two species. Concentration can be attributed to small ionic radii of these species as compared to thorium in 8-fold coordination. The pellets fabricated by cap process exhibited slightly higher expansion as compared to pellets fabricated by conventional route. And this is a note for the pellet fabricators, that pellet fabrication does have an impact on the thermal properties, and combined MD simulation and HT-XRD measurements indicate incorporation of uranium in thorium oxide systematically increases coefficient of thermal expansion coefficient. Rate of increase is higher in low uranium oxide composition range when it is less than 13%. Now, just the last part of my talk, thermal conductivity as evaluated by theory, by experiment compared with simulation. In this plots, you can, this is thorium oxide MD simulated thermal conductivity, this one, and then you also have the experimental values along with that, and you can see that the variation between the two is minimal, and therefore one can substitute for the other. And the same thing is listed here in form of table with A and B, as I told you in the previous view graph. There is an equation here which shows the thermal conductivity as a function of temperature. 1 minute. Yeah, so this is the equation where thermal conductivity is expressed as A and B parameters, and the same is listed here for the different alloys, both evaluated experimentally as well as theoretically, and you can see that the agreements are reasonably good and they can substitute for each other. So this approach of MD simulation is very useful for calculating the parameters theoretically without doing any experiments, and can be extended to other type of mixed fuels. This is for thorium uranium MOX MD versus experiment, the same exercise here, and the comments for these here, minor variations and the reasons for these variations are listed here. Now, finally, in conclusion, it can be stated that different routes have been developed for making thorium metal of different purities. I just showed you a flavor of that, and a detailed presentation will follow post lunch. Physical metallurgy aspects of thorium-based alloys encompassing phase transformation and diffusivities have been examined. I showed you an example of a thermocouple made, a couple made between thoria and zirconia for studying diffusivity, and some results on phase transformation. Actually, getting pure thorium is not so easy, because all the thorium that we end up getting does have some amount of oxygen, and only recently we have managed to get thorium which is reasonably pure in terms of oxygen content. Thoria is always very good with us, and that has never been a problem. MD calculated lattice parameters as a function of temperature for MOX are in good agreement with the HT-XRD data. The calculated thermal conductivities of thorium oxide and CO2 were almost comparable to literature data over the temperature range, and the experimental studies on thorium CO2 and thorium uranium for thermal properties show good correlation with theoretical modeling that we have carried out. So with that, I come to the end of my talk, and thank you for your attention.
Thank you, Dr. Dev, for a wonderful talk, and for the validation of your calculations through experimental studies. The floor is open. I will allow only 2 questions, and rest you can discuss during the lunch time. So for any clarifications, yes, Mr. Mehta, please.
Well, thanks a lot for this information. If one has to go for the long-term utilization of thorium, one has to do something with the irradiated fuel.
Yes.
And what is your status on that with respect to the properties and everything that?
You would mean change in properties with irradiation?
Yes.
Yeah, that's a very important point. And I would say that we have made a beginning in theory on both sides, that is theory as well as on the experimentation side. The experimental side on thorium is lagging behind, but in theory, I would say that it's possible now to generate data on the effect of irradiation on different properties. And I would say that it may not be very long before we would be able to tell theoretically what kind of differences in physical properties would take place with the radiation. Yes.
But you think that it should be verified by experiment by some irradiated fuel?
See, in this case, what we would like to do to expedite, we would like to do proxy irradiation because neutron irradiation has its own set of problems. We would like to do proxy irradiation and then see if the changes due to proxy irradiation, how different they are from neutron irradiation, and whether proxy irradiation can be effectively utilized for simulating the changes by neutron irradiation. And then we can do measurements, and that has less complication than an actual neutron irradiated material, which can be highly active. Yeah.
Thank you.
So this you just did mention one of the slide, thorium and other side zirconium diffusivity, and you did mention about that it leads to grain boundaries of thorium. Does
Yes.
it pose a challenge to fuel fabricators?
Yeah, it does. So that's what I mean. This kind of study is not numerous, and only now this kind of interactions are being studied. We have great relevance to when the fuel actually comes in contact with the clad and goes in. So though that has already taken place, we need to explore this because we haven't run thorium-based fuels for long lengths of time, and then the deterioration in the cladding and fuel failure will become important. So yes, it does diffusion and diffuse in, and how serious it is needs to be evaluated, and one may think of bringing some kind of barrier in between these two. Yes.
So as on today, we have a solution, or yet to look into some more, I would say, rather.
No, it requires further experimentation because if you want to put a barrier, then a lot of other things come into consideration.
Okay.
Yes.
Thank you.
Thank you. With no other clarifications, let us thank once again Dr. ThEC for a wonderful presentation. It's my pleasant duty to hand over a memento to you.